Welcome back to Electronics. This is Dr. Ferry. In this lesson, we'll be covering differentiators and integrator circuits. In our previous lesson, we looked at basic op-amp amplifier configurations, and those configurations in those circuits, we use just straight resistors. In this case, we're going to introduce capacitors, and by doing that, we're able to create circuits that differentiate or integrate the input. We'll also demonstrate the performance of these sorts of circuits using an oscilloscope on a real circuit. Let's start with the differentiator circuit. In this circuit, everything is based on the IV characteristics of a capacitor. I is equal to C dVc dt. We're also going to use the ideal characteristics of an ideal diode, which is zero current, an ideal op-amp, zero going into these two terminals, and then the voltage drop across here is zero. So let me go through and do a KVL around this right here, going up through this source, across the capacitor, through the resistor, and back out to here. And I'm going to treat this as being a voltage drop like this. So actually I go straight back down to the ground right here. So the KVL. Well, let's see. One thing that I can look at actually to simplify this, I'm going to do two KVLs. Let me do this one right here first. In this particular one, this voltage drop is zero, and this is the ground. So this actually is the ground right here. This is equal to zero potential. That means that Vn is equal to the voltage across that capacitor. And we'll define the current as going in this direction, so that voltage drop is plus minus V sub C. Now my second KVL is around this outer loop right here, and writing that I get minus Vn plus V sub C plus R times I, because all the current going through that capacitor must go in this direction since this current is zero in this little branch there. Plus V0 is equal to 0. Now this first equation still holds. In other words, these are equal. That means that this cancels out. And what I'm left with is V0 is equal to minus R times I. Well, I is up here, C dVc dt. Well, V sub C is equal to Vn. So that's where we get this equation right here. So this is now the equation that governs this circuit, the differentiator circuit. I want to show you an example of a real circuit that we've built to demonstrate this. And we're using a real op-amp chip right here. And that op-amp chip has 8 pins to it. And if you can look carefully right here, there's a little indent right up here. And where those indents are, that shows you that the one pin is going to be just to the left of it. It gives you the orientation. And there's a one pin 2, 3, 4, 5, 6, 7, and 8. That's how I know how to hook things up. In the 2 pin, we're going to be hooking up to V minus. Well, V minus is right here. So let me show that as a 2 pin right here. Where is that over here? Well, the indent is right here, so the 2 pin is right there. We count 1, 2, and that's V minus. So actually, let's start looking at this circuit right from the beginning. So we've got V in goes into the capacitor. So V in comes in, that's from my function generator, goes into one side of the capacitor. The other end of the capacitor goes into V minus, which is right there, the 2 pin. The capacitor also goes into the resistor, and the resistor is connected over to V sub 0. So V sub 0 is a 6 pin. I'm going to mark it as a 6 right there. So we should have a resistor going between the 2 pin and the 6 pin. So that's the 2 pin there, and there's a 6. So that's 1, 2, 3, 4, 5, 6. So that's the 6 pin right there. and that is connected to V0. Now, the voltage source to power this, we've got minus 15 volts connected to pin 4 and plus 15 volts connected to pin 7. We can see V sub S here and minus V sub S there. So this is now my circuit that implements this schematic. Let's look at the results here for the oscilloscope. If Vn is this voltage right there, and V out is this voltage. So if we look at this voltage here, V out and Vn. So it does differentiate. If Vn is a triangular wave, then if I take the derivative of it, I get a constant. And I'm actually going to get a positive constant, but then I negate it. So that's why it goes this way. So my output is equal to the derivative of the input. And I have a scaling factor in there, a gain, which is equal to minus RC. And that's whatever I pick. So I design my circuit with a particular value of RC in mind. Now let's take a look at the integrator circuit. The integrator circuit again uses the IV characteristics of a capacitor. But this time we're going to integrate this equation and get the integral form of the IV characteristics here. And that's what we'll exploit. So this circuit has a switch in it. And the switch opens at time equals 0. So prior to time equals 0, we have a closed circuit right here. We short out the capacitor. So for t less than 0, we want to write the equation. In that case, we can look at a KVL around here. And around here, we're going to use this ideal op-amp characteristic, which is 0 volts right there. So that means if that's 0 volts, and I've got a current I that we'll define as going through this resistor, that voltage across this resistor has to equal Vn. So Vn is equal to I times R. And also, I can do another KVL around this outer part, up through this voltage source, across this resistor, up through this, which is closed before time equals 0, and back down to here. And I'll do the same thing that I've done before just to emphasize the fact that I can finish this loop right here back down to ground. And if I do that loop, I get minus Vn plus IR plus V0 is equal to 0. Well, since Vn is equal to IR, these two cancel, and I'm left with V0 is equal to 0. Now for t greater than 0, the capacitor is now in the loop. So I can write a KVL going across that capacitor. I'm going to get the same minus Vn plus IR. Now I have to go through the capacitor, and that capacitor voltage is, I'll call it V sub C, plus V0 is equal to 0. Well, let me substitute in. Again, this part cancels out, and let me substitute in for V0 from here. So we get 1 over C, the integral from 0 to t of I dt is equal to minus V0. Well, I is equal to, we can solve from up here, I is equal to Vn over R. If I substitute that in for I, I'm going to get this equation right here. So this is the equation of this line where I take the input, I integrate it, I multiply it by a gain factor, and I get my output. Let's look at an integrator example. This is exactly like what we did before. The only thing different is I've switched these two components around. With the differentiator, we had the capacitor here. Now we've got it over here. So I've just switched these two around. And similarly, I've taken this circuit and I just switch the resistor and the capacitor around, and everything else is the same. So if I look at my results now, V in is right here, and V out is right here, and I'm integrating V in to give me V out. And I do have a little bit of clipping right here because it goes out of range. Remember, capacitors, or the op amps will saturate when the values get too large. So we get a little bit of clipping here due to that. But otherwise, what you're seeing is I'm integrating this constant to give me a ramp or a sloped line. So I am implementing this equation with this circuit. In summary, we have looked at differentiator and integrator op-amp circuits, and we come up with these two equations, these input-output equations for these two circuits. One is the differentiator and the other is the integrator. And I might mention that these two circuits were very important to early analog computers. Early analog computers, they used differentiators and integrators, and they used op-amps all through those computers in order to be able to do two things. One was integrate and differentiate values, and the other thing was to provide gain. So old analog computers full of op-amp circuits. In our next lesson, we will do active filters. Thank you.